We're back with the lecture videos for this week of Thanksgiving. We have a video lecture today and tomorrow. Make sure you remember to do your lecture questions after the lecture. All right, so the first thing is you're going to want to get out your notebook wherever you're keeping your information for Unit 4 on atoms. And we are going to be talking in these next couple sets of notes about the history of our understanding of the atom. It is important to know that right now we have a very complicated model of the atom because we've discovered so many things about it, but it has taken a lot of steps to get there. So we're going to go through the history of how the discoveries have shaped our understanding of the atom. So the first thing that we need to talk about before we get into the first person is we need to talk about what is a model. So if I asked you, and we're talking about scientific models, not runway models, what is a model? You probably have dealt with models of DNA or cells or the solar system, things like that. If you had to explain to somebody what a car looked like, you might get yourself out a little Matchbox car and say, hey, it looks a little bit like this. This is a model. It has wheels. If they've never seen a car, that you get into through the door, it drives, it makes noise, stuff like that. So a model is something that helps us in an attempt to understand or explain things. So that's what I would jot down. A model is an attempt to understand or explain things. And now you wouldn't need a model for like a pen. You would just be like, hey, here's a pen. You don't need a model for that. In science and in other things, we use models when we are talking about things like cells or the solar system or an airplane or things like that. We use them when we're talking about things that are too big or too small to actually work with. Okay, so models come into handy when things are too big or too small to work with. We are talking about too small. When we're talking about atoms, they are extremely, extremely small. And so obviously you can't just look and see what's going on. So we have models that we try to draw up to bring it up to a larger scale so that we can try to talk about how they work. The other thing about models that we need to make sure that we know is that if we have a model car, even the best model car, okay, if it sounds like a car and drives like a car and looks like a car and smells like a car and stops like a car and goes like a star, it would be a car. Any model that you have always falls short of reality, because if it was reality, then it wouldn't be a model. So the biggest thing is when we're going through some of these models, okay, even our best model of the atom does fall short of reality just because it's not reality. Okay, so probably if you were to ask a 2-year-old how to explain a car, they would probably have a very primitive understanding of the car, and the Matchbox car might be very good. It has doors and wheels and windows. That's good enough. But if you drive, you would probably say, well, it has to have a gas pedal and a steering wheel, and it has to have a gas tank to put gas in. So over time, okay, your model of your car, the things that you know about it would need to be included, become more complex. So the same thing happened with the atom. At the very beginning, we had a very primitive understanding of the atom, and therefore it wasn't really all that complex. But over time, and this is a huge idea because we're going to actually show you this, over time, models become more complex because we gain more information as we get new technologies, as we do more experiments, as we learn more things, and this is how things usually happen. Models become more complex because you gain more information. Okay, awesome. So we have models like this. This is a water molecule. It has 2 hydrogens, the yellow ones, and an oxygen. So the models that we have, this is good. Okay, even if we want to make it a little better, they sometimes people call water sticky because it sticks to itself. You can even add some like Velcro to these models to try to make it more realistic and things like that. But all models are going to fall short of reality, but they're our best attempt to help us understand or explain something. All right, so let's get into it. So now we're talking about the history of the atom how do we discover the atom? Who discovered the atom? All that kind of good stuff. And we have to go all the way back to the Greek times. So the first person you're going to want to write down and know, his name is Democritus. And obviously there's just a statue of him because he's way, way far back into the Greek times. Back in the Greek era, the main understanding was that matter was made of 4 different elements: earth, fire, wind, and water. And nobody was really thinking outside of that box except for Democritus. Democritus looked at things like, if I eat an apple, I grow. Or if something decomposes, a flower can grow from there. And that would be a little bit more like earth. But he was looking more at possibly the idea that if you cut something and you cut something and cut something and cut something in a million times, you eventually can cut it down so small, okay, that you can't cut it anymore. And then everything is made out of these little pieces and parts. And what he called these little things were atomos, or the word for indivisible. So he was actually the first person to be credited with recording this idea that everything might be made of atoms. Now, the only problem is that he had no proof. Okay, so the other thing you're going to want to know is that he didn't have any proof. He didn't have labs. He didn't have an electron scanning microscope. It's kind of crazy that he could even think about this and understand that everything was made of these small indivisible pieces, which we now call them atoms, for his an original term of atomos, because he was eventually right. So you don't have to write anything else on this slide, just getting the gist of the history. He wasn't one of the most famous, most relevant philosophers of his time. He was working around the same time as another gentleman you might know, and his name is Aristotle. Aristotle here, okay, Aristotle didn't believe, okay, in atoms. Aristotle still was believing the idea that it's earth, wind, fire, and water. He actually, while he was an extremely intelligent man, you might notice him. He's one of the front and centers in the House of Athens, the very famous picture by, or excuse me, the School of Athens, very famous picture by Raphael. All of these very smart, very famous Greek philosophers. Aristotle here, while he had a lot of things right, this was not one of the ones that he had right. He set us back about 2,000 years with him kind of tamping down Democritus, saying, no, you're not right. Not everything is made of atoms. So the kind of discovery of atoms went by the wayside for a very long time. Then we didn't actually just outright find atoms. What we found were a couple pieces of evidence to suggest that atoms might actually be the way instead of the 4 main elements. So we didn't find the atoms by themselves, but we started finding evidence. So I would label up evidence of atoms. And then we have Antoine Lavoisier. And you might want to jot down his work. It was in the 1700s. I'm not going to ask you the date or anything, but just so you can keep a relative running line of who did what when. And Lavoisier, if you know anything about last names, he is from France. If you know anything about French history, this isn't the greatest time to kind of be in France, I guess, depending on who you are. But so what Lavoisier was working on is he found it very interesting to do experiments in a closed container. So he would burn things in a closed container. He would do other experiments in a closed container. And what he found was that no matter what experiment he did, if the container was ultimately sealed, the mass would not change, whether you were burning it or adding something to it or whatever. Okay. And you guys probably know where I'm going. He ended up writing what's called the law of conservation of mass. And the law of conservation of mass, says that the mass before a reaction has to be equal to the mass after the reaction, as long as you've captured all of the reaction. And how does this lead us to believe that atoms exist? Well, what he started thinking about was the idea that, okay, if we just had earth, fire, wind, and water, it wouldn't necessarily break apart easy and come back together. What he was thinking is that if your beginning materials are kind of like puzzle pieces, okay? And so we have sulfur dioxide and water can make H2SO4 or sulfuric acid. if these were like puzzle pieces, and I could take an S from out of here, and I could add 2 H's from this over here, and then I could take my 3 oxygens over here, okay, and that everything was made of these little pieces, and that you can just rearrange and break down and make different things, and then you can take sulfuric acid and react it with zinc, and then it can just keep going. The idea of atoms being correct really started to pop up in his mind, okay? Now, in the height of when he was doing his work, also to make money, he was a tax collector for the government. And again, like I said, if you know anything about the late 1700s, that's when the French Revolution was. Anybody working for the government was not well liked by the public, and they actually beheaded him when they overthrew the government. Interesting thing is that they eventually found his work, found how amazing it was, and found he was really on the track to something, and they said, my bad. And so they put up a statue in his honor in France. You can still see to this day. They're like, whoopsie doopsies, sorry about that. So again, we could have had an advancement of atoms, but it was cut short. Again. So then we had to wait just a little while longer, because this is really one of the scientific heydays in the late 1700s and the 1800s here. Another person by the name of Joseph Proust was also doing some work at this point in time. Proust was working with water. And the idea was, so I'd write Joseph Proust, and I'd write kind of the date here. The idea is that France thought they had different water than other places in Europe, like Spain's water was different than England's water, and everybody had this special water. And what he did was he managed to do some water electrolysis, where you put a current through water and it breaks it apart. And the thing that he found is that every time you broke water apart, no matter what kind of water it was, it always had 2 hydrogens to 1 oxygen. 2 hydrogens to 1 oxygen. It didn't matter where the water came from. It was all exactly the same. And so what he was discovering is that all compounds are exactly the same no matter where they kind of originate from. So what he wrote was called the law of definite proportions. The law of definite proportions. And in the law of definite proportions, it says that, and I would just write the red part, compounds have a fixed and unchangeable ratio of its elements. Chemical compounds have a fixed and unchangeable ratio of its elements. So the idea is that every salt molecule, no matter where you mine it from, NaCl, 1 sodium, 1 chloride, that's it. Every carbon dioxide that is breathed out, no matter who's breathing it, has 1 carbon and 2 oxygens. The law of definite proportions. This just helps to kind of support what Lavoisier was already saying in the idea that probably everything isn't made of these 4 primitive elements. They're probably made of atoms. Okay, so he went on to do his work with the law of definite proportions, and that helped us get a step closer. Awesome. Then we come to our last person of the lecture today, and his name is John Dalton. We're again written the early 1800s here. If you've heard of any history of the atom, most people start with Dalton. You might have heard it if you took a physical science before this class. And what Dalton did was he wrote a theory, okay? And it's called Dalton's atomic theory. Dalton was an extremely smart individual. He was just extremely poor at this point in time. So he didn't really have access to education. So while he was trying to go to school, he had to drop out when he was 11 and try to get an income for his family. So he got a job. He wasn't very good at keeping jobs. But then when the local school teacher passed away, he was so intelligent that they actually hired him back at the age of 12 to become the school teacher of his community. So with that, he got into education, and then people were inspired and saw how intelligent he was, and then he got scholarships, and he eventually went to university. He was notoriously bad in the lab. He would break things. He was just really bad. So what they said was, how about you just think? Okay, you just think about things. So he didn't get to actually do any experiments, But what he did was he had the ability to put a whole bunch of information together and package it really nice and then deliver it to people in a way that they accepted. And so we really, really start with the idea of an atom with his theory. His theory has 4 parts, so we're going to jot those down. The first part of his theory said that all matter is composed of atoms. Okay, so as you can see, he goes ahead and gives a little nod to Democritus, and he says, all right, you guys called them atomos or indivisible in Greek. All matter is made of atoms that are indivisible and indestructible. So he kind of took Lavoisier's idea of, hey, we think that everything must be made of these little pieces and parts that rearrange, but they're not lost or created. Okay, so all matter is composed of atoms that are indivisible and indestructible. Then the next 2 pieces of his theory are not exactly like brain busting, but everything had to have been learned. So this might seem very simple to you, but somebody had to say it first. So with this idea of an atom, his idea was that all atoms of the same element are identical. So that means every oxygen atom that you find are exactly the same. And then the oxygen, or every chlorine atom are exactly the same. Okay, so all atoms of the same element are identical. Then, wait for it, all atoms of different elements are different. So that oxygen atom is not the same as the chlorine atom. So again, you probably understand that. That makes sense to you. You get that. However, somebody had to be the first person to kind of realize that. And then the last thing, he kind of yanked a little bit of what Proust said. His 4th kind of postulate in his theory is that compounds are composed of 2 or more different elements in a definite ratio. And that's pretty much just taking exactly what Proust said and putting it in his own theory, but still, it was nice. So compounds are composed so that water is always H2O. Your sugar is always C6H12O6. Everything has a definite proportion. Okay. So as we're going through with this, you're probably still writing some of these down. His theory was so well liked and so easily accepted, and you don't have to write this down, we're just talking, is because number 1 was quite simply the law of conservation of mass, which everybody already agreed with. And the last one was just the law of definite proportions, which was also widely accepted. So he just kind of packaged up everything we already knew and wrote a theory about it, and then the idea of atoms were born. Well, again, after Democritus. So everybody said, okay, all right, so atoms, everything's made of atoms. Great, lovely. We need a model. What does an atom look like? And Dalton didn't have anything except for the idea that atoms existed. So what Dalton said is that an atom must look like a marble. Okay, just a sphere, no pieces, no parts. And so I would absolutely know this about it. This is where the model of our atom kind of came from here. Just a marble. So the first model of the atom we have is a marble. Okay. Obviously, we know now that there are pieces and parts. You just took a quiz on protons, neutrons, electrons, all that kind of good stuff, but we had to start somewhere. So thank you very much, and then tune in again tomorrow when we continue our journey on the history of the atom. Feeling blessed, never stressed. Got that